Hello, yes, I'm actually Pittman. I work at DDA. I actually live in Europe, so it's quite a local conference for me to come to, which is nice. Excuse me. So, file system fragmentation in Lustre. It's not something we normally hear a lot about, but it can cause problems on occasion. So, firstly, what is file fragmentation? It's been known about for years. Certainly, historically, it's been a problem in local file systems. And what it is as the file system starts getting full, you find that individual files have to be written to smaller blocks. Which should be all well known for a long time. That affects new files that are written when the file system is fragmented, but also you then have this legacy problem that even if you defragment or recover space in the file system, you have a set of files on the disk that themselves are fragmented, so you have poor read performance. So this is a stock image I found. It's actually really difficult to find this kind of image anymore because fragmentation isn't generally a particularly hot topic. This is a Lustre tool that I found that does ext4 fragmentation. But it's kind of rare, it's difficult to compile, it's not even in Red Hat or it's not even in Gen 2, so it's not generally regarded as a popular topic. The reason it's a problem is when you get spinning media, you've got the SATA drives. They're good for capacity. They've got good bandwidth, streaming I/O, large writes. Everything is fine. You get a lot of bandwidth and it all adds up, and you get the headline numbers you're looking for. But they're very poor for seeks, and unfortunately, with the file fragmentation, the seek performance becomes the dominant factor. So there you've got large I/O available, large bandwidth available, you haven't got the IOPS, so your bandwidth actually suffers even though the drive is capable of delivering. Not just the actual drive, but also as the drive gets, so not just the space on the drive, but also as the drive gets full, you've got the cost of the block allocator, which is an important factor to consider in this. You might have a block allocator that's perfect and manage to get everything block aligned, but if it takes a long time to do it, then you've still got the slowdown, you've still got the performance issue on write. This is actually a graph. It took me a long time to get this graph. I tried to measure it and measure on a single OST or on a single ext4 file system the cost of fragmentation. It should actually say effective fragmentation. It doesn't cost 100%, but you can see the effect. These are real numbers, but I had to sample something else and then kind of work backwards mathematically to get this graph. I'm slightly worried it might not show because on my laptop it only comes up as 1 pixel, but it looks like it's 2 or 3 pixels there. For a single OST, generally, for a local disk with ext4, for a single OST, it doesn't matter. The x-axis across the bottom is space utilization as well. At lower space utilization, it's not an issue at all. It's only when you get to around 80% that you start seeing a measurable effect, and then it's negligible. This is why it's not a particularly hot topic. And if you remember, I had a lot of effort finding a graph, finding the picture of it, because it's really not particularly interesting. So, why does it become an issue on Lustre? Well, Lustre doesn't just use one OST. If it did, you wouldn't be using Lustre. Lustre uses many OSTs. You get lots of performance by taking lots of OSTs and adding them all together. Made the mistake there. You don't add them all together. When you get lots of OSTs, the performance of all the OSTs is not the sum of the performance of the OSTs. It's actually the performance of the slowest OST multiplied by the number of OSTs. So if you do, the example I've used here is 60. So if you do 60 reads and one of them is slow, in effect, because you're waiting for all of them, in effect they're all slow. So a single OST, a slow OST can have a dramatic effect on performance. But then, unfortunately, scalability is never easy, and pure maths works against you. So the likelihood of one OST being slow is actually much worse. I looked into the maths behind this as I was doing this talk, and it's much worse than I thought it would be. But actually, you take the probability of one OST being slow and you have to raise it to the power of the number of OSTs. So larger OST counts become a real problem. So if you take the previous graph and just render that same graph but on a file system with 60 OSTs, then you get that, and that's exactly the same data, but just for exactly the same underlying data, but just calculated up for 60 OSTs. And it's a real measurable effect. We've had several customers come to us that have rerun the acceptance tests, sort of 6 months or sometimes even years into production, and they're not getting, the numbers that they paid for and initially saw. And I see one customer that's grinning at me now, but they remeasure it, and maybe they get 75 or 80% of the performance, and we look into it, and because of this is actually causing a real problem. When I said I had to calculate the single OST numbers, they're actually calculated back from this graph. This graph is the one that I was able to reproduce, and it's one that we've seen on real systems in around this. This is simulated data, but we've seen it on live systems with a very similar trend line, very similar effects as well. So, how to avoid it? Well, this is OST utilization, so every yellow bar here is the number of blocks used on an OST, so every yellow bar is an OST, and then the percent of space used. This is a file system, it's about 65 to 70% used. Every OST uses the same amount. Very little fragmentation between the OSTs. They're very likely getting full bandwidth here. If the threshold for losing performance through fragmentation seems to be around 75 to 80%, but it obviously depends significantly on the type of usage you put your file system through. So this is a good file system. They're getting very, there's no reason to believe they won't be getting very good performance still at this level. This is another file system, similar number of OSTs, slightly more usage. It's a little bit more uneven, but again, you've got to believe. I look at that and think actually this file system is probably unaffected. It probably doesn't have a problem. This is another file system we've got in a customer. Slightly interesting graph because it's got the big step in it there. We think this customer is using OST pools, so they have the data on the right is allocated to one group, and the data on the left is allocated to another group. But if you look at it, they're running at about 90% capacity, and they've got 20 out of 30 OSTs at 90% capacity. So at that stage, it's very likely that they will get fairly significantly reduced performance on when writing to the left-hand side of the file system, possibly in the sort of 15 to 20% reduction in write performance, and indeed read performance for the files that have been newly created. And this is just about the worst one, where if these people had allocated their data accurately, they'd be using about 70%, so they'd be back to the first graph, and I'd say they were unaffected. But actually, they've got some OSTs that are sort of 95% full, will be really suffering and driving down the performance of the whole file system. So although these people aren't using a lot of capacity proportionate to other people, they will be disproportionately affected. So, obviously you should try and avoid this situation, but sometimes people find that they've hit this problem normally when they do a performance measurement and find out it's not what they're expecting. So what can you do about it? Well, firstly, rebalance files, so bring the utilization level to the OSTs back to a common baseline, try and level everything off. This has always been possible to some extent if you're aware of who's using the files, because you can simply copy them and then replace the original with a copy. That's slightly difficult because it's unsafe against other users using the file at the same time. So you need to be sure that your users aren't doing that when the admin performs the operation. It's now possible in 2.4 to do it safely without having to get the OK from the users first. But that only works with the space available. And the other option is reduce usage levels, which is basically delete data. Not a universal solution, that one obviously, but you know, sometimes it is good. You know, sometimes it is a viable option, and we have had customers who have hit this problem and have solved it that way. So how to avoid this in the first place? Well, you know, avoidance is always better than fixing it. So, you know, if everyone bought file systems that were twice as big and only used SSDs, it wouldn't be a problem. But I find that very unlikely to happen for fairly obvious reasons. Don't consume all the space on the file system. This is actually fairly typical. People normally buy bandwidth rather than capacity. All the numbers that you see banded around, and certainly the headline figures all tend to be bandwidth. And you need the spindles to get the bandwidth, so space tends to almost be a secondary concern. So, you know, not using all the space is a very reasonable solution for many people. And if you don't go above 70% and you do monitor it quickly, it's almost certainly not a problem. So you can reduce the cost of the fragmentation by limiting small files. Ideally, this should mean that the block allocator has a better chance. It's got less work to do. There'll be the bigger blocks available. Or you can hit higher usage levels without hitting per OST fragmentation problems. So keep the OST utilization flat. I avoided that. Avoid large unstriped files. I'm not quite sure why what the main use case for unstriped files is. If they're large, then they should really be striped in order to get bandwidth. But if they're not, if you have large files that are unstriped, you know, they might actually be contributing to this problem because they'll be skewing your usage levels. An interesting conversation I had yesterday was actually, you know, larger block allocation sizes would potentially solve this entirely if everything was done in sort of 16 or 32 meg chunks and all the files were that big, then this would be much less of a problem. Another interesting idea, which we haven't tried in practice, but potentially has a lot of benefit, is only striping to a subset of OSTs. If you've got, say, 60 OSTs and you set your default stripe to be 55, then the Lustre load leveling policies would naturally avoid any OSTs that were uncharacteristically full, and that would, and as I said before, they tend to be the slowest OSTs, so that would avoid the worst of the problem. And it's entirely reasonable to believe that on a file system like the last one that I demonstrated, that a write to a subset of the file system will be faster than a write to the entire file system. It's a slightly interesting idea, and I quite like to prove it to see if that's true. But certainly in theory, that it should be possible to do that. I haven't made any distinction between reads and writes so far, but I did have an interesting idea that writes will always be affected, and that you tend to do large writes. It's unusual to do a write and think as soon as this write is finished I can start some computation, whereas if you're doing a read, then it's more likely that you're going to do the read and do some data with it. So potentially, if you are just reading the file and doing some data, potentially using a number of smaller reads, aligning your reads with your stripe sizes, obviously, but if you did a number of smaller reads and waited for them all in turn, then the reads would complete at different rates, which it do anyway, and the application would get an individual notification of the reads. So even if you just ran through your data sequentially, you could start reading every block as it arrived without having to wait for the slowest block. If you wanted to go further, you could actually read them in the order that arrived, but that adds significant complexity. Again, this is just a query. Don't go off and rewrite anything on the back of this, but it's certainly something that could be looked at if you do find that you want to make sure you're getting the full bandwidth in these cases. So as I said earlier, the quick fixes and the avoidance problems are fine, but even when you have rebalanced your file system, you've created new space and you're back actually getting the full write bandwidth. You've then got a subset of your files on disk that are spread out over non-contiguous blocks on the disk, and they will get persistently bad read performance for the lifetime of that file, which is very, very difficult to find. And we actually have found a few instances of this, but it's not too easy to do. Certainly impossible to benchmark, but I guarantee it's there, and I guarantee it's causing problems even though you can't actually see them directly. However, if you can, when you've identified the files, or when you've identified a candidate file, there's a very easy way of telling there's a file frag command. It just comes with Lustre, and it just dumps a sort of hexadecimal block of the file index, the block index on the disk, and then the OST index. So you can sample an individual file and tell if it's affected, and make a prediction if you're going to be losing read bandwidth when you access that file later in the future. So that's very good. It's actually a very useful command to have. But it only works on specific files. So after you've detected this problem, taking steps to rectify the new files, what can you do about the existing files? Well, you need to find them. You need to find them and then you can sample them, and then when you've sampled them and confirmed the problem, you can fix it. So you're looking for large files. You're looking for files that are almost certainly striped. If they're large and not striped, then why not? You probably know a specific date range, certainly know the end date range. You might not know the start date range, but certainly you can narrow it down to some kind of range you're looking for. And also, potentially have a candidate OST list. So you might want files that are created in the last 2 weeks that encompass OST 18 and are striped above a certain size. Now, Lustre has a fairly standard user interface called POSIX, which doesn't support that kind of query very well. So, although we have experienced this issue in the field, none of the customers that have experienced this and suffered from it have actually had any way of finding these files, because there are LFS find options that you can use to do this, but we're talking about mature file systems that have been in production for a while. By definition, they're nearly full. So, the time taken for the LFS find is prohibitive, which is really unfortunate. There is, in theory and in the lab, certainly we've done work with Robinhood where actually we set up a file system, put on Robinhood, created a load of files, created fragmentation, detected the performance drop, deleted the files again, and then gone into Robinhood, standard SQL query, and identified the files and gone in and then actually found files that were affected and managed to do a read on them, do a copy of that file and do a read and see performance improvement. But you need Robinhood to do that. And the people that have had this problem haven't had Robinhood, and retrofitting Robinhood to large, historic file systems is time consuming and not something that we were able to do in these particular cases. So the conclusions, problems that are solved and are non-issues in the single case become huge issues. In the power case, it's well known in HPC. It's my background is networking. Exactly the same things apply. So maths, probability maths is just against us, and scaling gives problems. Best practice can avoid the issue in most cases. That's true, but we've seen it multiple times, so it is a genuine issue. As I say, people often don't see it. We had one customer that we think had probably been suffering for this and going to reduce bandwidth for quite a period of time, and it's only when they do a software update and rerun the acceptance testing that they see the problem. Unfortunately, you never actually run the acceptance benchmark before you do the update, so the performance drop-off gets blamed on the update, not on the contents of the file system. It's really, really easy to diagnose if you've got monitoring in place. And you don't need a lot of monitoring, but you do need some monitoring. You do need to keep an eye on it. You do need to know where your file system is. There's a fairly easy fix for new files. So if you find yourself in this mess, there is something you can do to resolve it in the general case, but you might still have these lingering problems. And then just this last issue, potentially block allocation potentially changes to block allocation could help solve this issue, could help avoid it. I just put in a slide here about ZFS to head off any questions. It will be different in ZFS. Everything I've done is all my members are LDiskFS. It's Lustre 2.1, 2.1.2, and 2.1.3 if people invested. Lustre will be different. It's got a different write policy. It's copy on write for overwriting files, and also has fewer OSTs, so that probably helps. But it's still mass driving this problem at the end. You've still got scalability problems, so the same problems still apply, although to different extents. My prediction is that it still exists. And that's it. Any questions?